Kia ora everyone. It's a great pleasure to be back here again and enjoying the Taiwan International Geothermal Conference very much. And thank you very much to all the organisers and all the participants. I'm going to talk today about how we understand reinjection and production from our geothermal systems, where there's an aggressive and exciting program of development in Taiwan, and managing those resources is going to be critical to achieve those goals. So I'm going to run through the processes that we go through for managing geothermal production and reinjection. So to manage your resource, this is going to be not just in terms of energy production, but for obviously the economics, social and environmental drivers are all important for managing your resource. And this is true whether it's a conventional geothermal system or EGS as well. So I'm going to focus mostly on examples from conventional systems because, as we all know, EGS is just come through the pilot stage at the moment. It's complicated because of the high uncertainty in the subsurface and dynamic conditions. You can have multi-phase fluids, boiling and chemistry that make it challenging. And the key tool that we use in the geothermal industry for managing the resource in terms of production reinjection is reservoir modelling. And in New Zealand, along with other countries as well, in the permitting and planning process, you need to demonstrate your sustainability of your project using reservoir modelling. So it's not just good for doing your management of the project, but it's an essential part of the permitting process. So I'll just very quickly talk about reservoir modelling. We use an integrated reservoir modelling approach at the Geothermal Institute, where we pull together all of the knowledge from the geological, geoscientific, geochemistry, geophysical studies, and we tightly couple that to our reservoir models so that our reservoir models represent the best understanding of the geothermal systems, and it includes all of that expert knowledge and data as accurately as we can. And then once we have a good reservoir model, we can use it for all of these factors: the resource characterization and risk mitigation. We can optimize the well targeting and design, optimize the production and reinjection strategies, which I'm talking about today, and also manage those environmental impacts with good modeling. So the reservoir modeling allows us to do that because it's representing the full physics and reservoir behavior, and so we're able to then use it to assess these different aspects, which I'll talk about today. So the main things we do is production, how to manage production and reinjection. If there's future development of the system, we use modeling to do that as well. Investigating the sustainability or environmental impact. And then another key point of the reservoir modeling is that essentially they're digital twins, and we can also look at how to improve monitoring using the modeling as well to see how we can monitor what's happening in the system better. Model calibration, again, this is, you can spend, I come into New Zealand and spend a whole semester doing a course on building and calibrating models. But basically the idea is we want our reservoir model to be able to represent the true system and reproduce the production data, geoscientific data, and the early stage data as best as possible. So, and these are the sorts of matches we're looking to match pressure trends over time, temperature measurements downhole, and production trends as well. Once we have a good match, we assume our reservoir models are a good representation of our system. A key factor, though, is always remember, all models are wrong, but good models are useful, okay? So your model is always going to have assumptions, but if you build it well, follow best practices, take into account all of your geoscientific data and your production data, then it will be very, very useful tool. And that data is key. So this is from our colleagues in Iceland. This is a nice representation of all the different types of data that we would expect to be able to capture and represent in a good geothermal reservoir model. You know, from the geological data, borehole data, geophysical data, well logging, geochemical, well testing, and then all the way through to conceptual model data and administrative data. So a key takeaway there, the data is really important. You know, if you're going to make robust decisions about production and reinjection and managing your resource, then good data is really important. The modeling relies on good data, and start gathering the data as soon as you possibly can. It says day one there, but we mean day one of your project, not day one of production, but before you drill your first well, before you even have started applying for drilling permits, you should be trying to gather data in your project. And you know, there's lots of different systems for managing and storing data, and it's worth thinking about those systems early as well.
Is there value in having integrated data management across the full suite of activities, from drilling through production to correlating that back to reservoir life?
Absolutely, absolutely. Unfortunately, there's no standard for that right now in geothermal, and so that's you know, larger companies develop their own integrated databases. Unfortunately, sort of the off-the-shelf integrated databases from mining or oil and gas aren't quite fit for purpose. Well, they could be, but there's definitely something, as a global industry, that's something that we're working towards. Yeah, absolutely. But there's the earlier you can put some of that in place, the better. Yeah, absolutely. So a couple of key things. Remember what your reservoir models can and can't do. So they're very, very good at predicting where the hot fluid is going to be most likely to be and where the good average permeability is likely to be. But everyone who's worked in geothermal for any length of time knows you can drill a very successful well in a project and then 10 meters away drill another well which is unsuccessful. There's so much subsurface heterogeneity, and it will be exactly the same here in all of the settings in Taiwan, means that that can happen. So modeling can tell you where it's the best place to drill on average, but it won't tell you the probability of drilling success exactly. It won't tell you exactly where to drill the well. It'll tell you how to plan it so you get the best chance of success. We can do very good predictions of future well behavior following initial well testing, but you can't know ahead of time exactly how a well is going to perform as well. We can't predict problems with casing and cementing with reservoir modeling, but we are able to do important things like investigate uncertainty quantification with good reservoir modeling now as well, and I'll talk a bit more about that. In terms of operations, we can't predict operational problems or mechanical failures, human error. I had a project I once worked on where the client, the management team got taken over by an accountant, and the accountant said, why are you suggesting drilling make-up wells now that the price of oil has dropped so much and it'll be cheaper for us to burn heavy fuel for this project? And I said, well, if my reservoir model could predict the price of oil, I probably would be a very rich man. I wouldn't be doing this. So, that's not the things that reservoir models predict. We can couple our reservoir models with techno-economic analysis, and we do that in our projects so that you can plan contingency for resource availability and plan for operational effects like scheduled downtimes or even unscheduled downtimes. But don't expect that reservoir models will predict those things for you. Okay, so this is the kind of thing. This is from one of our big projects in New Zealand, where, you know, we work with the management team and the reservoir team looking at using good models to forecast all of these different scenarios for developing different parts of the system. So we're looking at the, you know, total takes from the system, and looking at different scenarios for taking different amounts from different wells, looking at how the enthalpy or the essentially the energy or temperature decline over time, and looking at steam flows for different options for whether we close the power plant or build a small new power plant or a large new power plant. And this is a critical job that we do with reservoir models. Another one might be, this is an example of a different project where we're actually just looking to sustain a current level of production. And so the reservoir models tell you how many makeup wells you're going to need. And these are different scenarios looking at where we place the different makeup wells, how productive we think those makeup wells might be depending on the planned drilling technology. Are we going to drill wide diameter wells or typical wells? Optimizing reinjection strategies is another key and standard use of reservoir models, and it's going to be critical in Taiwan going forward, planning how this is going to work using good reservoir models. And this is just an example. It's not very surprising, but basically with no reinjection, we have the fastest decline in our production because we don't have pressure support, but we have the most stable production enthalpy or temperatures. When we move to our in-field reinjection, we get the most pressure support, so the best production, but we see the highest level of decline in our enthalpy and temperatures. And then the outfield reinjection is kind of a mix of the two. We get some pressure support, and we see less temperature decline, but then eventually we do see that thermal breakthrough coming through. And this is a key tool, is using reservoir models to help plan this in your system. A new thing that we've been doing, pioneering at the Geothermal Institute, is running these forecasts with uncertainty quantification. It's a technique that we've copied from oil and gas and groundwater modeling as well, but applying it to geothermal has some unique challenges, and we're very proud of how this new tool is going to be able to support the industry going forward, which means that we're now able to make forecasts. These are examples where we're running thousands of models, and you can see in this case we're able to sustain the target power out to 2050 before some of the models show that there's a possibility of some decline. And then at the higher target of 260 megawatts, we can see, you know, it's much more powerful being able to tell the decision makers, you know, we're 90% sure that we can sustain that out to 2037, but, you know, we're only 10% sure it'll make it out to 2045. So this is giving the decision makers ranges of forecasts is going to be become standard, and it's much more powerful than the standard reservoir modeling. And this is just an example, again, another example showing the with a case with and without investment. And one of the interesting things to see about this is because we're without investment, the uncertainty is much lower because we're dealing with wells that we already understand relatively well. There is still some uncertainty about how the decline will happen. This is, you can see the P90, P10, P50. But then you notice with new investment, increasing productivity from the system, we see much more uncertainty. And that's because you're drilling into areas that are unknown. And so being able to give this sort of information to decision makers is going to be really critical when you're drilling into new areas like will happen in Taiwan. Another thing we can do with this new technology is this is actually taking thousands of realizations of the reservoir model. We can not just look at things like power production, but we can look at the likelihood of where the boiling zone is And in this particular case, we were really interested in where this liquid level was, because we knew that the deeper liquid was acidic. And this tells us the probability of encountering steam or liquid. And so in this case, the idea was, well, let's make sure we don't drill any wells deeper than 500 meters below sea level, because in all of the thousands of realizations of models we ran, all of those models had steam at that elevation in this location. So this is a kind of innovative new technology that we can use reservoir modeling to support the effort in Taiwan. Another advanced tool we're using reservoir modeling for as well is in partnership with the Geothermal Technical Office in DOE in the USA and Lawrence Berkeley National Lab is looking at critical minerals extraction from the Salton Sea. And we've also applied this in another resource in Italy. And this is all around including in the models those estimates of how much of these rare minerals are in the geothermal brines and how much you can extract. A couple more slides. CO2 reinjection is going to be very important in Taiwan. In New Zealand, we've been pioneering that as well. So in our conventional systems, several of our conventional systems, we now do full reinjection of CO2, and understanding where that CO2 is going, how long it'll stay in the reservoir, what impact it might have on your production is going to be very important. So this is another exciting.
Is that for artificial lift or for sequestration?
Well, for both, it does have an artificial lift effect. At the moment, it's the New Zealand industry are doing it for not for sequestration, but for carbon neutrality. But we do have a project because there is a certain amount of CO2 that is produced often. Depends on the system, but for some it's not insignificant. And so this gets us to truly net zero. And then it also, but we do have a project looking at net negative, so carbon sequestration in active geothermal systems. And we fully expect that there is, what we've seen already is there can be a artificial lift benefit to it. But you need to manage that, right? So you need a good model that's going to do a good estimate of the flow paths. So key takeaways, reservoir modeling is your critical tool for managing your resource, planning your production, reinjection, and it's going to allow us to assess those economic, social, environmental impacts as well as the production and injection strategies. It's key to have good data and as much data as early as possible. And we now, as I've just demonstrated, we're able to use reservoir modeling also to support these more advanced applications and geothermal uses as well. Tēnā koutou katoa. Any questions, please? Sure. Yeah.
So some people use the model treat as gross media, and some people use the actual process system to simulate. So do you have any comment on these two different approaches? And for the CO2 sequestration, I have a follow-up question about where's your resource of CO2?
Those are very good questions. So for a conventional geothermal system, the best practice is a porous media, but we often do porous media in a dual porosity approach where we are representing fast fracture pathways and matrix where we allow some thermal non-equilibrium. And the reason why that is the best practice is that to model and understand a conventional geothermal system properly, you need to model a very large area. You need to model all of that recharge and all of the full convective system properly, which just isn't practical with a DFN at this computationally at this stage. Smaller scale for an EGS, the preference would be a DFN, but once you get into tens of kilometers squared to model a full convective system, that's not practical. And it also raises running DFNs. You either need a method to have a very good characterization of your DFN, or else you need to run massive ensembles of models to account for the fact that you don't know what your true DFN looks like, so you need to statistically account for that. So those are the reasons why at this stage best practice is still porous media with dual porosity for conventional systems. For CO2, there's all kinds of options. In New Zealand and potentially in Taiwan, I suspect we have a very good managed forestry system in New Zealand, and there is a certain amount of forestry waste that is a good source of then CO2 essentially. So burning wood slash or wood pellets, you could actually, what we're looking at in a project which is supported by the New Zealand government in partnership with the University of Canterbury in New Zealand is, perhaps increasing enthalpy of fluid with some boiler, extra heat from burning wood slash, capturing the CO2 and then also sequestering that as well. So, yeah, but any industrial processes that are producing CO2 could be used for a net negative approach.
Thank you. Thank you also then.